compare the radio telescopes and the Hubble Space Telescope, which is not radio telescope. So
yeah. So if I had a radio telescope, a single radio telescope that was the size of the Hubble telescope, it would make very blurry images because the wavelengths of radio waves are very long compared to the wavelengths of light waves. And remember that angular resolution gets bigger when the wavelength gets longer, which means it gets worse. So a radio telescope the size of the Hubble telescope would make really, really blurry images. But when you combine radio telescopes across continents, you can make images which are much more finely detailed than Hubble Space Telescope images are because of using such widely separated telescopes.
So it doesn't necessarily the 500 times bigger than Hubble telescope.
You can do much better, yeah. You can do much better. Now it's at radio wavelengths rather than what the Hubble telescope observes. So you're looking at something, you're looking at a different part of the spectrum, but nevertheless, it allows us to make very finely detailed images. And that, for example, was behind our ability to make that image of a black hole you might have seen. Interferometry was used to make that image of a black hole at the Event Horizon Telescope, for example. You need interferometry to get that kind of detail. Did you have a question you were asking?
I was just curious, if it's possible to do that, why have we not put 6 radio telescopes on each end of the Earth?
So we do make various combinations of radio telescopes. And one thing that's being left out of this is there are advantages to having a whole range of separations of the radio telescopes, because it turns out that if you have just 2 telescopes, you can see very fine detail in terms of sharp edges, but larger scale structures you don't see very clearly when you do that. So you need a whole range of separations to see the full range of different size scales in what you're trying to study. And that's why the Very Large Array has lots and lots of telescopes. You do better with multiple telescopes with a range of separations than you would with 2 single telescopes. And yeah, we do that. We do use radio telescopes across Earth to do interferometry like that. Yes?
So does that mean that if you increase the distance, you get a better?
You do. As you increase the distance, you get a finer and a more and more finely detailed image. And that's why we like to use very long baseline interferometry. With these, they're on tracks that are spread out like in a triangle, so not a triangle, but 3 legs. And so they allow them to spread out along there, and so they get the finest resolution when the telescopes are as spread out as possible. But again, it turns out it's also helpful to have other separations as well, because an image actually contains information at very fine details, but also information at larger scales as well. And you know, if you watch YouTube videos carefully, YouTube compresses their videos, if you watch like music videos, such that when you see a relatively uniform background behind people, you might see that it has a very limited number of shades that it shows. It doesn't show fine gradations of color or shading behind them. And that's because it's missing detail at kind of medium size scales. And that's what happens if you only use widely separated telescopes in your interferometer. And so it helps to have a whole range of separations. You get more detail at all scales if you use a lot of separations for the telescopes. Again, I certainly don't expect you to understand the mathematical details of that. But yes?
I have a new question.
Okay, you have a new question. Yes.
Could you distinguish between reflecting and refracting telescopes?
I sure can. It's really simple. If it's a refracting telescope, it uses a lens as the main light gathering element. And if it's a reflector, it uses a mirror as the main light gathering element, because lenses refract, bend light that passes through them, and mirrors reflect light that falls upon them. Yes?
Could you explain why the wavelengths of an element's spectral lengths appear the same whether their emission or?
Yeah, it's because the same energy levels are involved. You know, why does an element have the same wavelengths of emission and absorption? It's because it just depends on which direction you're going. So here's the energy level diagram for hydrogen, for example. And if an electron starts in the ground state and a photon with 10.2 electron volts of energy comes along, then that atom can absorb the photon and use its energy to jump up to level 2. And so if I have lots and lots of hydrogen atoms, and there are photons coming in with 10.2 eV of energy, you'll get an absorption line at that wavelength because hydrogen atoms can do a good job of absorbing those photons. By the same token, if you have a hot gas of hydrogen atoms with a lot of electrons in level 2, they can drop down to level 1 and give off photons with exactly that same amount of energy, 10.2 electron volts. So in other words, absorption lines are when electrons are jumping up levels, and those are caused by that. Emission lines are caused by electrons jumping down to lower energy levels. And because a given atom has exactly the same levels that electrons can jump up to, or jump up between, or jump down between, you get exactly the same wavelengths that it's good at absorbing light at and good at emitting light at. That's what it comes down to. Yes?
Yeah, the advantage of the reflecting telescope.
Yeah, so why are all the world's big telescopes reflectors? Yes?
And the fourth advantage of your presentation.
Mm-hmm. Yeah, so let me.
Here's what further into the violet.
Yeah.
Spectrum.
Right, so this slide right here, yeah. So get out of the way.
So does it mean the refracting telescope, if we launch the refracting telescope into space,
Mhm.
we cannot detect the infrared?
So the Hubble Space Telescope can observe at infrared and ultraviolet wavelengths because it uses mirrors instead of lenses. If it used a lens in the front instead of a big mirror, the lens would absorb ultraviolet light that the mirror is able to reflect. The lens would absorb infrared light that its mirror is able to reflect. Even on the ground, some ultraviolet and infrared light make it to the surface, and a mirror can work with those wavelengths that a lens cannot, because the glass is opaque to ultraviolet wavelengths and infrared wavelengths that mirrors are still able to
So
reflect.
can you say it for X-rays and gamma rays?
That's a different thing. Reflector, this is really, here we're talking about optical telescopes, ones that work at wavelengths that our eyes can see or close to that, like so-called near ultraviolet and near infrared wavelengths. That's what this is really referring to. Yes?
So you're saying that mirrors obtain more wavelengths than lenses?
They can see, yeah, they can be used at a bit wider range of wavelengths than lenses can. That's not the most important advantage they have over lenses, but it is an advantage that they have. We can use them at some ultraviolet and infrared wavelengths that a lens would block the light from, so it wouldn't be able to be used for that. Now, you take advantage of that with like wearing glasses, because eyeglasses and sunglasses protect your eyes from ultraviolet light, because the plastic or glass in them absorbs ultraviolet light while it still transmits visible light, so you can see just fine through them, but it protects your eyes from ultraviolet light that isn't able to make it through the lens. So it's a nice side effect of wearing glasses, is it protects your eyes from ultraviolet light. Get into the plain chicken stage. Yes.
So in comparison between the emission and absorption in electron volts. So the absorption is bigger when it jumps between more energy levels?
That's whether you're talking about absorption or emission. In other words, the amount of energy that is either absorbed or emitted is the difference in the energies of the two levels. So for example, back to this diagram, okay? If an electron were to start in level 3 and drop down to level 2, or vice versa, start in level 2 and jump up to level 3, the energy involved is the same in both cases. It's 12.1 minus 10.2 electron volts. So this transition, either absorption or emission, is 12.1 minus 10.2 equals 1.9 electron volts. But if you go from level 4 to level 2, that's more. Now it's going to be 12.8 minus 10.2, 2.6 electron volts. So this transition, 1.9 electron volts, is a red spectral line. This transition, 2.6 electron volts, is a turquoise colored spectral line. You see different colors coming from the hydrogen lamp when I had you put the diffraction grating in front of your eyes, because different jumps by the electrons are corresponding to different amounts of energy in the photons. Yes?
Could you go over velocity, acceleration, and force?
Sure. So they're all vectors. That means not only do they have bigness, so-called magnitude, they also point somewhere, they have direction. So what do we call the bigness, the magnitude of velocity? What's the everyday term, or even in physics? What the bigness of velocity is called? I think I heard you starting to say
Speed.
Speed, yeah. So
Okay.
speed is the magnitude of velocity, how big it is, but it points somewhere. So two cars that have the same odometer reading but are driving in different directions have the same speed but different velocities. Not in everyday English where we're casual about it, but in physics, in strict physical usage, they have the same speed but different velocities, because while they're moving as fast as one another, they're not heading in the same direction. Acceleration is change in velocity, which means that you could be changing the speed or the direction of motion or both. So if you're changing either the speed or the direction of motion, that is acceleration, and it requires a force to bring it about. So that, for example, if I'm speeding up, that's acceleration. If I'm slowing down, that's acceleration. If I'm moving at constant speed but on a curved path, that's also acceleration because my direction is changing. If I'm speeding up and changing direction, that also is certainly acceleration. The only way not to be accelerating is to be either not moving at all relative to whatever you're measuring your speed with respect to, or moving in a straight line at constant speed. Anything other than not moving or moving in a straight line at constant speed is acceleration and requires a force. And acceleration is also a vector. It points in a direction. Force is also a vector. Not only does it have size, it also points in a direction. Yes?
Is radial velocity is how many moments elements or?
It's the other way around. So radial velocity is the motion that is towards you or away from you. So in other words, picture would look like.
Why is it velocity plus?
Yeah, well, because it's used sloppily, is actually what, it's a velocity component.
Yeah.
So here's 3 stars, this one is moving directly away from Earth, all of its velocity is radial velocity. This star is moving perpendicular to the line from Earth to the star, and so that means none of its velocity is radial velocity. Its radial velocity component is 0 at this moment. This star has both radial velocity, it's partly moving away from Earth, and what we call tangential velocity, partly moving perpendicular to the line from Earth. So basically, if I'm walking right towards you, all my velocity is radial velocity. If I'm walking perpendicular at some moment, then I have no radial velocity. If I'm going like this, I have some radial velocity, but not all my velocity is radial velocity. Only if I'm moving straight at you or straight away from you is all my velocity radial velocity.
So why do we separate actual velocity and radial velocity?
Yeah, because the Doppler effect only depends on the radial velocity. So this star would have no Doppler shift. This star would have maximum Doppler shift given whatever its speed is. And this star would be somewhere in between. If all these stars were moving the same speed, this one would have the most Doppler shift, this one would have no Doppler shift, and this one would have some Doppler shift, but not as much as this one because not all of its velocity is radial velocity.
My question is why? Because it just has two directions. It can have.
You mean like why does only the radial velocity matter? Is that what you mean?
No, I mean, why you can tell it as a velocity instead of, because it just have huge, it could have just huge.
So are you asking kind of like an English usage question?
Yeah.
Yeah. Because we are not always precise in our use of language, is the answer to that question. Yeah. What it should really be called is the radial component of the velocity vector. But that is a mouthful, and so even physicists get a little sloppy and say radial velocity instead of the radial component of the velocity vector. And that's really all it comes down to, just being a little sloppy. Yep. Sorry on behalf of English speakers everywhere. Yes?
So you said that the Doppler effect relies solely on the.
Only the radial velocity matters, yes.
So on the stars, number 3 would still show a Doppler effect.
It
but
would.
Not a major one compared to number 1.
Right, if they're all moving the same speed, 3 will still show a redshift because it's getting further from us, but not as big a redshift as star 1 does. Yep. This is why when you drive towards a radar gun sign, a sign that measures your speed to tell you slow down, you may notice even if you're moving at a rock steady speed towards the sign, if you're not speeding up or slowing down, the number on the sign changes. And that's because if you're the sign and I'm driving past you, as I get over here, less and less of my velocity is radial, and so you'll typically see your speed appearing to drop on the sign even though you're not changing your speed. Because as you start to pass the sign, a smaller and smaller part of your velocity is radial velocity, and it's only able to measure your radial velocity. Which works to your advantage if you're going a little over the limit and the cop is using the radar gun because they don't quite see your full speed. Unless you're driving right towards them, and that's not a friendly thing to do. They don't like that if you drive right towards them. Yes?
Is that also?
Oh, sorry, I'll get you in just a second, sorry. Yes, go ahead.
Is that also why a perpendicular motion will produce a Doppler shift?
It does not produce a Doppler shift because there's no radial component to it. It's all side to side instead of in or out. Yes? Yes, question?
So if you drive past the cop and then the person that hits the brakes, does it seem like their speed's even lower than what it was?
You mean like you hit your brakes while you're driving towards them, or?
Yeah, I mean, I guess like for when you like are kind of like near them, you're decreasing in speed as you're going.
If you're hitting your brakes, they will see that too, but you will appear to be slowing down more than you actually are, because part of it is coming from you're actually slowing down, and part of it is coming from the radial component of your velocity getting smaller. Right as you drive past the cop, they can't see any speed from you because you're moving perpendicular to the radar gun speed. Yep. Now, I do not advise, oh boy, I better speed up so I'm perpendicular to the cop as soon as possible. That's not going to work. They'll notice you went too fast before you got there. Yes?
What does it mean to ionize an atom?
It means to split an atom off of it. It means to have a collision between two atoms that gives enough energy to an electron to kick it off the atom, or a photon can also have enough energy to kick an electron completely off the atom, and then you're left with a free electron and an ion, meaning an atom that has a positive charge because it doesn't have as many electrons orbiting the nucleus as there are protons in the nucleus. Yes?
So the thing that splits off, it doesn't exactly have to be just an atom, it could be an electron or.
So typically what we'll talk about being ionized is an atom or a molecule. So splitting an electron off of an atom or a molecule is ionization. And what's left behind is a positive ion and an electron that is now flying free, no longer bound to an atom or a molecule. It's going rogue. I want to see what my phone is doing right now. I hope it's still recording. It's probably pretty low on the battery because making videos is pretty intense. What do we got? Ooh, 1 hour, 39 minutes. Yeah, let's see. What's the battery say? I don't know. Apparently I'm zooming in instead. Okay, I'll just risk it. Yeah. Okay. And we're back in focus. Hi, everyone. Scared to have my phone. Dr. Harmon, I missed the exam because I had to go to the hospital because you suddenly appeared large and upside down in the video, and I couldn't handle it. That's not going to work. You guys are here. He said he's going to ask the perfect question. If I leave, I won't see it. Yes.
I don't understand why wavelengths of an element's spectral lines are the same, whether they appear as emissions or absorption.
We did that. That's the idea that it's because it's got the same set of energy levels to jump up and down between. So if it jumps up to an electron, if it jumps up to a level that's 2 eV higher, a bunch of atoms doing that will make it to the EV absorption line. A bunch of atoms jumping down to a level that's 2 eV lower, between the same two levels, if they're separated by 2 eV, those atoms will be making a 2 eV emission line. The wavelengths and energies are determined by the levels they're jumping between, and for a given atom, it's got the same rungs of the ladder that it's jumping between. That's really what it comes down to. So think of when I had the ladder in class one day, and I was saying if I go up 2 levels, that's a green photon. Well, if I go up 2 levels, I'm eating a green photon, and if I go down 2 levels, I'm spitting out exactly the same wavelength green photon. So all that matters is the energies of the levels for the given atom. It's got the same levels to jump up and down between. Jumping up causes absorption lines, jumping down causes emission lines.
it just mean the electrons, electron go away, or
Yep.
just
That's exactly what it means. So in other words, this, my little picture would be, here's a nucleus. Here's an electron. Of course, they don't literally orbit the nucleus. They're in quantum wave functions or whatever, but forget that. Here's this electron orbiting the nucleus. A photon with enough energy comes along and boom, it flies away. That's ionization.
Is there a different name which represent the situation, which is
The inverse of ionization is called recombination.
the process of becoming a plasma?
So a plasma is a gas that is ionized. So in other words, a plasma is a gas where atoms in it have been ionized so that, like on the sun, there are free electrons not attached to any atom, and ions, atoms that have lost electrons. And in the sun, there's also neutral atoms that have not been ionized. But a plasma is a gas where atoms have lost electrons through ionization. So it's an ionized gas is a plasma. Yes?
Is there a point, like, can an electron, is there a max amount of energy it can absorb before it finally, if it's too much, it just won't even accept the photon?
No, there's not a maximum energy that it can absorb. The way it works is that, if I go back to the hydrogen diagram here, okay? So, suppose that the electron starts in the ground state, okay? Could it absorb a 5 electron volt photon? Nope, because there's no 5 eV level. Could it accept a 10.2 electron volt photon? Yep, you could do that. How about 10.3 electron volts? Nope. Next one would be 12.1 electron volts. It could accept 12.8 electron volts. It could accept whatever this energy is. See this 13.6 electron volts there? That's the limit. That's the limit where if a photon comes along with 13.6 electron volts or more, the electron can absorb it and leave the atom as a result. That's the ionization level. So there's no maximum energy that it can absorb. There is a maximum energy such that it can't stay attached to the atom anymore if it absorbs that much energy or more.
That makes sense.
Mm-hmm. Yes?
Is it possible to the ionization comes first before becoming the plasma?
Ionization is what turns a gas into a plasma. So in other words, when I have those spectrum tubes and I turned it on and it starts glowing, do you remember that in class where I had a hydrogen tube and then I turned it on? Before I turned it on, it was just a gas in there. When I turned it on, the gas became a plasma by becoming ionized. So at low temperature, if you take a plasma and cool it down, the electrons will do the opposite of ionization. They will recombine with atoms. So a free electron can be like finding a positive ion and say, hey, let's make an atom, okay. And it can be captured again. So that's the inverse of ionization, is called recombination. And at low temperatures, the atoms all have a full set of electrons, but as you increase the temperature and they move faster and faster, collisions become more and more violent between them, and you get to the point where many of the collisions have enough energy to strip electrons off. And also, if it's hot enough, there might be photons that have enough energy to strip electrons off. So it's not that first there's ionization and then it becomes a plasma. Ionization is what is turning a gas into a plasma. And there are degrees of ionization. You can have a highly ionized plasma and a very slightly ionized plasma.
it is gas, the ionization is exactly in the plasma. It's becoming plasma.
So ionization is turning it, is what turns a gas into a plasma. When it's ionized, it's a plasma. If the atoms are not ionized, if they're neutral, if they have as many electrons as protons, then it's just a gas. Yes.
So as far as the idea of falsifiability, that just means that if you can't prove your hypothesis false,
Then it is not scientific. No, it doesn't mean if you can't prove it false that it's true. It's that for a hypothesis to be scientific, it needs to be possible to show that it is false. You need to be able to do an experiment or do observations that would show you that it is wrong. And just because you haven't done so doesn't prove that it's true. But in other words, the reason we demand that you be able to prove it's false is simply because it's impossible to prove something is true beyond any possible doubt. Observation. You might just not have figured out how to prove that it's false yet.
but if you prove it's false, then why don't we just change the hypothesis?
You do, yeah. If you show it's false, you gotta throw the hypothesis away or modify it. Absolutely, yeah. If you falsify, so for example, we might hypothesize that the reason why day and night happen on Earth is that the sun is going around the Earth. Well, people used to think that, but then it was shown that that's not really the way to look at it, right? It's Earth is rotating is the reason why, Earth is spinning is the reason why night becomes day, becomes night, becomes day. So that you can have a scientific hypothesis that turns out to be false. And when that happens, you need to replace it. You need to find another hypothesis. The point is that if you have a hypothesis which you could not show was false, it's not a scientific hypothesis. For example, if you were to claim that the reason why thunder happens is that there are gnomes that create thunder whenever there's lightning. How would you show that that's, and the gnomes always hide from, I'm being ridiculous, but the gnomes always hide from humans so that we can never see those gnomes, but those are the things that are making the thunder. That's not falsifiable. If we could never see the gnomes, we could never find out whether or not that's false or not.
So doesn't that just mean that falsifiability is whether or not you can actually test it?
Yes, but it's strongly related to that. It's a statement about what it is distinguishing between is, yes, you have to be able to test it. You're testing it to see whether or not it's false, okay? It has to be possible to show that it's false. The reason why we put it in those terms is because in general, it's impossible to show that it's true beyond any possible doubt, because maybe we just haven't tried all the possibilities. So for example, go back to Newton's law of gravity, the one that says force is g times mass 1 times mass 2 over distance squared, right? So how can we test that? We could take a bunch of masses and try a bunch of different distances between them. No matter how many masses and distances we try, we haven't tried all of them. For example, maybe I try them being 1 centimeter apart and 2 centimeters apart and 3 centimeters apart. Maybe I do that for 1,000 different distances. There's still other distances I didn't try. I didn't try them for 2.5 centimeters apart. I didn't try them for 9.6443 centimeters apart. I can't possibly try every possible distance and show that it always works. If I try many, many distances and it always works, it makes me confident that it's correct, but I haven't absolutely proved it because there's distances I haven't ever tried. Falsifiability, on the other hand, is much easier in that I don't have to perform an infinite number of tests to show that it's false. If I just have one really good experiment and it doesn't work, I have shown that it's wrong. So one experiment can show something's wrong, but in general, it would take an infinite number of experiments to show that it's always, always, always right. So falsifiability for logical reasons is doable, where proving something inductively via experiment and observation is not doable in an absolute sense. I think that that's worth thinking more about, but I wouldn't lose sleep over it right now. You know what I mean? In other words, in terms of getting ready for the test, I don't think that I would obsess over worrying about that distinction. Just understand that falsifiability is required for a hypothesis to be scientific. It has to be able to be shown that it's false.
So is it required for theories to be falsifiable?
Theories need to be falsifiable to be scientific theories, yes.
And models?
Models also, to be a good model, it ought to be something where you could be convinced that it's not a good model, that it doesn't work, essentially. On the other hand, you have to be, it's a little subtle though, because nobody thinks that a model made with balls and sticks of a molecule is correct in every sense. So there, it would be more along the lines of what if I thought that a good model of a water molecule was the oxygen was in between the hydrogens and they were all along the line. It turns out, no, there's actually an angle between the two hydrogen atoms in a water molecule. And so this would not be a good model. But that's not to say that this is a perfect model. I mean, obviously a water molecule isn't a giant O with, isn't an O with an H and two lines between them, you know. So,
Could be falsifiable, but
yeah, but it's right. It's you have to have some flexibility in interpreting what it means, essentially. Yeah. So I think I'll probably, you can ask more questions, but I think I'll turn that off because I don't,
Thank
you know, because I don't want them to keep thinking, if anybody's watching this, oh my God, it's 4 hours long or whatever, you know, so,
you.
yeah, so.